This lesson is about inverse functions. Before we discuss inverse functions, however, we need to discuss a type of function called a one-to-one function. And a function is said to be one-to-one when every item in the domain corresponds to exactly one item in the range, and every item in the range corresponds to exactly one item in the domain. So let's get some bubble charts of functions, these function diagrams, that is. I have a set of values that I'm referring to as my domain and a set of values that I'm referring to as the range. We mentioned in the past how a relation can be described as a function as long as every item in the domain corresponds to exactly one item in the range. So for instance, if I connected the value 5 with -1, 8 with 0, -2 with 2, and 3 with 5. This would be a function. But it's not necessarily a one-to-one function unless the reverse is true. So now that I've come up with my function, I can try and decide if it's one-to-one by looking the other direction. So for instance, 5 is corresponding to -1, and -1 in the range only corresponds to 5 in the domain. 0 only corresponds to 8 in the domain. 2 only corresponds to -2 in the domain. 5 only corresponds to 3 in the domain. So this relation is not only a function, but it's one-to-one. Let's look at another example. Same set of values, but I'm going to change the relation between the domain and the range. So I'm going to correspond 5 and -1, 8 and 0, -2 and 2, 3 and +2. This still qualifies as a function. All right, so it's a function because every single item in the domain corresponds to exactly one item in the range. So it qualifies as a function. However, when we go the other direction, -1 corresponds to 5, that's great. 0 corresponds to 8, that's fine. It corresponds to only one value. But 2 corresponds to multiple values, which means that this is not a one-to-one function. So it's a function, but it's not one-to-one. So it basically has to be a function going from the domain to the range and from the range back to the domain. So you really have to have a very nice setup similar to what we had here in the first example. Now the bubble charts are nice to help understand, but when it comes to actually working problems through, they're not necessarily the most usable. So one thing that will help us is that a one-to-one function will pass both a vertical line test and a horizontal line test. So for instance, let's look at this graph. This graph will certainly pass a vertical line test because there's no vertical line that I can draw that will pass through the function at more than one point. Similarly, there's no horizontal line that I can draw that will pass through the function at more than one point. It looks like around here, if I drew a horizontal line, that possibly would occur, but it's really just due to the scale of the axis that it looks that way. In fact, this graph does only touch at one point, and you could see that if you zoomed in a little bit further in that region. So because it passes both a horizontal line test and a vertical line test, this is a one-to-one function. Let's look at this example. This will pass a vertical line test, because there's no vertical line that I can draw that will touch the graph in more than one spot. However, there's a whole bunch of horizontal lines that I can draw so that it will fail the horizontal line test. So it passes the vertical line test, fails the horizontal line test. So this is a function but not a one-to-one function. So a one-to-one function is important because these are the only functions which possess a unique inverse function. And there are some important functions that are not one-to-one, but can have an inverse defined using a strategic domain restriction. This works when the graph of the function possesses some vertical axis symmetry. Let's explore the concept of inverse functions. An inverse function is one that effectively works in reverse. It undoes the operations performed by a function by turning the order of the operations performed around. Essentially, it maps the range of a function onto its domain by swapping x and y values. The notation that we use for an inverse is f to the negative 1 power of x, which we read as f inverse of x. And it's kind of an unfortunate notation because students at first think of, like if I had 2 to the negative 1 power, that would mean 1 over 2 to take the 2 down into the denominator. And so often students will think that f to the negative 1 power of x is equal to 1 over f of x. And I'm writing this in red because it's wrong. It doesn't work that way with functions. It does work that way when it comes to numbers, but not with functions. So let's look at what happens with functions. So back to some bubble charts. Let's suppose I have a function f of x, and I'm going to define a relation between my domain and range, and that's going to be my function f of x. Okay? Now, the inverse of f essentially reverses the order and swaps the domain and the range, because the input into f inverse of x are range values from f of x, and the output is domain. So for instance, let's say I put the value 5 into my function f. 5 maps to negative 1. So the result is negative 1. So if f of 5 is equal to negative 1. Going the other direction, f inverse of negative 1. So now the input of the inverse is an output of my f. But it takes me right back to the original input, which is 5. So that's why negative 1 is in the domain of f inverse of x. 5 is in the range. Similarly, 0 would map to 8, 2 would map to negative 2, and 5 would map to negative 3. So these are essentially just swapping the domain and range of the original function. Let's take a look at some more concrete examples where we're actually finding some inverse functions. One piece of information that I want to point out that will be useful is the rule that f of x is equal to y. So f of x and y are always interchangeable. That's how we define our graphing, on a two-dimensional plane. Now, in order to find the inverse of a function, you can swap the x and y variables and resolve the equation for y. So as I mentioned, an inverse essentially just swaps the domain and range of the function. The domain are the values along the x-axis, the range are the values along the y. So we're just swapping those values, which is why the rule here states this is how we solve for an inverse. So let's see how it works. So if I have f of x equals 2x minus 4, then that's the same as y equals 2x minus 4, because as I mentioned, f of x is equal to y. Now we swap our x and y. So when I swap x and y, my function now looks like x equals 2y minus 4. Now I'm going to resolve the equation for y. So when I resolve this equation for y, then I'm going to add 4 to both sides. So x plus 4 equals 2y. Then I'll divide both sides by 2. So x over 2 plus 2 equals y. This is now my inverse function, but I just need to express it as f inverse of x equals x over 2 plus 2. All right, let's try another example. F of x equals x cubed plus 5. So that's the same as y equals x cubed plus 5. Now when I swap my x and y, I end up with x equals y cubed plus 5. And in order to resolve for y, I would need to subtract 5 from both sides. So that gives me x minus 5 equals y cubed. And to get rid of that cube, I could just take the cube root of both sides. So the cube root of x minus 5 is equal to y, which tells me my inverse, f inverse of x, is the cube root of x minus 5. So as you can see, it's definitely not just taking the function itself and putting that in the denominator. So it's not 1 over x cubed plus 5. The inverse function in this case invokes a cube root instead of a cubing, because the cube root is the inverse of a cube. So you have to be careful. Here's another example. H of x equals x squared minus 4. Well, this is kind of an interesting example in that it's not a one-to-one function. We use squared functions all the time, but the graphs of these are parabolas, and the graph of a parabola, like in this case, it might look something like this. Parabola shifted down 4 units. It's not one-to-one. It fails the horizontal line test. But there is a thing that can help us. Because this graph possesses a vertical symmetry, meaning that if I split the graph right down the center here, it looks the same on one side of that vertical axis as it does the other. We can actually just restrict our domain to 0 off to positive infinity, and that would result in just this part of the function. And that's enough to get all the different values for our inverse, because the other side of the graph is just the negative of each one of those points. So for instance, this point right here, that it has the coordinates x, y. This point right here just happens to have the coordinates negative x, y. So it's just the inverse of that. And that's perfectly fine. So we can get away with this. But we have to restrict our domain to the interval from 0 to positive infinity. And when we do that, now we can just say this is y equals x squared minus 4, or y, I'm sorry, I need to swap my x and y. So when I swap x and y, I get x equals y squared minus 4. And now I resolve for y. So x plus 4 equals y squared. And this is the point where we would get into trouble if we didn't have this domain restriction. Because the thing about this is, when I take the square root of two sides of an equation, I have to consider the positive and negative square root. So y equals the plus or minus square root of x plus 4. Which is what I would have to do without that domain restriction. And you can see that all the y values are just negatives of each other, because it's plus or minus the same number. But with that domain restriction, all of my x values are positive, which means the result of everything in this square root is going to be positive. So we don't need to worry about the positive or negative. So this is just a function now. So I get f inverse of x is just the positive square root of x plus 4. And if you graph this function, I'll draw it very small over here, so I'm running out of space. This is a square root graph that is going to be shifted to the left by 4 units. So I'll just bring it back here like this. And if you'll notice, that square root graph is only defined from -4 to positive infinity in the domain, and the range is 0 to positive infinity. So it also has restrictions of its own, and we're going to explore its restrictions in just a few minutes. But for now, let's do one more example. And this one is very similar, but it involves absolute value. So the graph of absolute value, in this case absolute x plus 1, you have this V shape. And everything is shifted up 1 unit in this case. So again, there's this vertical axis symmetry where if I just restrict my domain from 0 to positive infinity, then I have the exact same set of points on the right-hand side of this as I do on the left-hand side. So I don't lose any information because of that symmetry. So what this means is if f of x is equal to the absolute value of x plus 1 on where x is going from 0 to positive infinity, if x is a positive number, then we don't actually need those absolute value bars. Because if we know that x is positive, then if we take the absolute value, we just get x right back out. And if I swap my x and y, I get x equals y plus 1. Then I'll subtract 1 from both sides. So x minus 1 equals y. Which means f inverse of x is x minus 1. Now, this function is also restricted, but again, we're not going to talk about that restriction just yet. We will get to it in a moment. Let's first look at how inverse functions work. So, if I have the function f of x equals 3x plus 7, it's a linear function. It's most definitely 1-to-1. So I can get an inverse for this function. Let's do that. So y equals 3x plus 7. Swap the x and y. So I have x equals 3y plus 7. Resolve for y. So x minus 7 equals 3y. Y equals x minus 7 over 3. So that tells me my inverse is x minus 7 divided by 3. Now, let's take a look at how this works by using a couple of points. So I'm going to use just some randomly chosen values. How about -1 and +2. I'll start with 2. I'm going to plug x equals 2 into f of x. So that's going to be f of 2 equals 3 times 2 plus 7. 6 plus 7, which is 13. And I'm going to take x equals -1, plug that into f of x. So 3 times -1 plus 7. So -3 plus 7 gives me +4. So I have 2 points. I have the coordinate pair 2, 13 and -1, 4. Okay, now my inverse function, let me bring it down here. All right, so down where I can use it. Okay, here's my inverse function. Now, what I'm going to do is turn things around. So I'm going to put the 13 into my inverse function and see what happens. So f inverse of 13, I get 13 minus 7 over 3, which would be 6 over 3, or 2. So on my inverse, I have the point 13, 2. So if you notice, the 2 was that original x value that I put into my function. If I put 4 into my inverse function, then 4 minus 7 divided by 3 is going to be -3 divided by 3, or -1. It gets me right back to that original value. So let me compare the inverse to the original function. So f inverse was this, f of x, 3x plus 7. So I'm looking at just this part right now. Anytime I put an x value in for f, the first thing that I do is multiply by 3 and then add 7 to it. F inverse does the exact same operations, or the opposite of those operations, in the opposite order. So f of x, multiply by 3, add 7. F inverse of x, subtract 7, divide by 3. So the opposite operations in the opposite order. That's how it undoes what the original function does. That's why you'll always end up just swapping your x and y values. Let's look at a property. So a property here states that if I compose f and f inverse of x, I get my original x value back out. And it doesn't matter what order I do this in. So just to verify that this is true, let's go back to the pair of functions that we just were looking at and see what happens when we compose these functions. So if I do f composed with f inverse, then what that means is to evaluate f of x at f inverse x, or to evaluate f of x at x minus 7 divided by 3, which means I would take 3 times x minus 7 over 3 plus 7. So I'm just plugging that into f of x. Now the 3's cancel, and I have x minus 7 plus 7, which cancel, and leaves me with just x. So this essentially says if you put a function into your, if you put a value into your function f and get a y back out, then take that and put it into your inverse, you're going to get right back to the original x value that you started with. It'll happen every single time. Let's look at graphs of inverse functions. The graphs of inverse functions are interesting because they are symmetric about the line y equals x. This stems from the fact that we swap the x and y variables in order to solve for the inverse functions. So for instance, if I have some function f of x, and I'll just sketch in a function here, and I want it to pass through that point AB, then every single point that's on f of x gets swapped, x and y values get swapped and relocated on the other side of the line y equals x. So for instance, this point AB gets relocated to the point BA. Every single point gets relocated to an equivalent point on the other side of the line. Any point that crosses the line is shared. So essentially, this graph down here ends up looking symmetric to the original graph, but it goes in a different direction because it's flipped about the line y equals x. But these distances to the line that are perpendicular are preserved. Oops, I missed my point, but those distances are preserved. So essentially, the thing that you want to take away here is that the graphs of inverse functions are symmetric about the line y equals x. So let's graph the function f of x equals x squared on the restricted domain from 0 to infinity, and I meant that to be a bracket, so I want to include 0, along with its inverse function f inverse of x equals square root of x on the same set of axes, and identify their domain and range. Okay, so f of x equals x squared we know is a parabola. And ours is restricted to the domain 0 to positive infinity. So that's what I've drawn there. Now, the graph of the square root of x, actually, tell you what, let me identify domain and range. So of f of x, the domain is 0 to infinity, and the range is also 0 to infinity. Now, the inverse of f of x is the square root of x. Now, we know what the graph of the square root of x looks like. It's essentially a parabola, but it's laying on its side. And so, if you'll notice, we are kind of seeing that same symmetry. For my inverse, I have a domain from 0 to positive infinity and a range from 0 to positive infinity. I should label this f inverse of x. But if you'll notice, the line y equals x would be like right through here, and we are definitely symmetric about that line. Okay, that's going to happen with every single set of graphs that are inverses of one another. One thing that you don't really see here, because the domain and the range are the same, is that the domain and the range of inverse functions essentially get swapped. Let's take a look at the next example to see how that works. So the rule is that the domain and range of inverse functions get swapped. So for instance, if this is my function f of x, I want to identify the domain and range of that function. So the domain starts at 1 and goes to positive 3. So for f of x, the domain is the set from 1 to 3. And I'm going to erase all this stuff as I determine the domains and ranges, because otherwise the graph will get too much stuff on it. All right, the range is the values along the y that are possible for the function to produce. So starting from +2 to a maximum of 4, but not including the 4. Now, let's take a look at the inverse of this. So this point here, let me do this in green. It has the coordinates 1, 2. It's going to map to the coordinates 2, 1. This open circle here has the coordinates 3, 4, and if it gets flipped along the line y equals x, it will switch to 4, 3, which is right there. The rest of the points along the way, a similar thing happens, and we get basically the exact same image of a graph, just on the opposite side of the line. Now, let me look at the domain and range of the inverse. So this is my inverse function. I didn't draw that very well. Let me try again. That's my inverse function. Its domain starts at 2 and goes up to +4. So for f inverse, the domain goes from 2 to 4, but not including the 2. Its range goes from 1 up to 3. So if you look at the domain and ranges for f and f inverse, they've just swapped. So the domain of f is now the range of f inverse. The range of f is now the domain of f inverse. They've just swapped from each other. And that relationship will always hold true between any function and its inverse.